So welcome to session 3. So we're going to kick it off with Ned Taylor. Take it.
Hi. Ooh, is that too loud? No, okay, I'm going to have to try and modulate. So how many people have heard of Foremost before? A few, good. All right, so this is really loud and freaking me out. Is there a speaker volume that I can turn down a little bit? Is that, yeah. Okay, so this is showing essentially the magic of Foremost. So these are the 2400 separate, Foremost is a multi-object spectrograph system. So these are the Foremost fibers reconfiguring into the Fabulous Four, Fantastic Four, whatever it is, logo, but giving you the sense that it does that very quickly. All right, let me begin by admitting that I'm not really a cosmologist. I'm really a galaxies person. But have now co-lead this project, the Foremost Hemisphere Survey 4HS, with my very good friend, Michelle Kluver. And so by way of introduction, let me tell you a little bit of my worldview and how I came to 4HS. So the starting point is low redshift science can be either driven by or limited by the availability of redshifts. So the Sloan Digital Sky Survey was a cosmology survey that was supposed to measure BAOs. It got maybe 10 papers out of that, at a guess, but it got something like 3,500 other papers just by virtue of having redshifts, right? So you can think about all of this science that might not have been done had it not been for the cosmology project. Then my first postdoc was on a survey called Gamma. What Gamma did that was different was assembled all the photometry that it could possibly get, so from the ultraviolet through the optical, the near-infrared, the mid-infrared, the far-infrared, and beyond, for a very well-characterized sample with total spectroscopic completeness. It was the first survey to go from what I would call a survey, right, where you just go and you ask a bunch of people a few questions, to a full census, right, where you get the full amount of information that you can get from every galaxy to get a really complete picture of each and every galaxy and all the components in it. I've said low Z a few times. What do I mean by low Z? I propose an operational definition for low Z. Low Z is where a photometric redshift is not helpful, right? You can imagine a galaxy at 0.1, and there's you've got a photo Z error of 0.03, which would be really good. That means there's a 1% chance that galaxy is behind you, right? So photo Zs in the low redshift universe don't carry enough information to tell you the distances that you really want, and the error propagation gets hard and whatever. So by this definition, spectroscopic redshifts are essential for low redshift science. Okay. With that as background, can you imagine a universe in which we have LSST down here, we have Euclid down here, we have Roman over all sorts of places, but you've got Y's everywhere, SKA down here, but especially Rubin down here, but all of the redshifts are in the north, right? Can you imagine that we have all of these amazing surveys concentrated in the south, but are unable to do low redshift science for want of spectroscopic redshifts? That was the problem that we identified, and so what we want to do is make sure that we live in a universe that looks like this. So this is the 4HS sample. These are the galaxies that we hope to get spectroscopic redshifts for. So that's how we came to 4HS. But it turns out that if you want to propose a large project, it's really handy to be a cosmologist, because writing a cosmology proposal is really easy. You can say, I'm going to measure this number to 5%, and people go, great. But if you say, I want to get 4 million galaxy redshifts, they say, why not 2 million? Why not 5 million? Justify your number. Yeah. I will come to the cosmology science goals of 4HS, which were really helpful in a minute. So Foremost is many things, but one thing, Foremost is a project to re-outfit the VISTA 4-meter telescope on Paranal to turn it from a near-infrared imaging telescope into a multi-object spectroscopic survey facility. And so, you've got to put in a fiber system and all of this stuff, but it's purpose-built as a spectroscopic survey facility that will run for 5 years to an average depth of 2 hours over the sky, over the full southern hemisphere. It was really sold as a GAIA follow-up machine, but it can do so much more. The magic is this tilting spine positioner. So there's 2,400 of these little spines that each carry an optical fiber that go off and feed 3 separate spectrographs. The real magic is that these fibers can move in seconds. So between every observation, you can reconfigure to look at a whole different set of targets. So you can just go boom, boom, with 1,000 redshifts or 1,000 spectra at every moment, or 2,000 spectra at every moment. The crazy thing, which makes sense, which sounds really good until you think about it, is there's a mixture of high resolution and low resolution fibers across the field. The high res ones are really good for stars, and especially for bright stars, and the medium resolution ones are good for everything else. The reason this sounds like a good idea is because you can pursue many projects at once, right? So it's very efficient, is the idea. The trouble is, because no single survey can use this instrument at all, everybody has to be using it at the same time. So Foremost is also a consortium of many different science projects that throw all of their targets into the bucket, and then the machine will just go through and select targets and dole them out 2,400 at a go. Of the first 5-year survey, 70% was allocated to 10 consortium surveys, with 30% reserved for what are called community surveys. So this is people who can propose their own project, and 4HS was one of these. Getting all of these surveys to work well together is, let me say, an operational challenge. It's an organizational challenge. It's a political challenge, but it also presents some unique opportunities, including for 4HS. So if you wanted to do a big spectroscopic survey of the South, what do you need? You need a very large field of view, tick, Foremost is perfect. You want that rapid reconfigurability so that you can go quickly from one set of targets to the next, tick, great. You want a very high fiber density, tick. You want a minimal exclusion radius, right? You want to be able to get your fibers as close to as close to each other as you can so that you can get pairs and all that kind of stuff, tick. And you need stellar partner surveys. Why? Because galaxies are clustered, I want to be able to make sure that I get all of them. I need to go back a couple of times to get the hard to reach ones. And I need other people to be using the fibers while I'm doing that, right? This is why Sloan, for example, had this pairs problem, not because they couldn't go back enough times, but because if they did, they would only be using 1 or 2 fibers, and it becomes very inefficient, right? So doing this within the Foremost consortium survey carries these big advantages and is what lets us do very high completeness. Scientifically, we add to a whole bunch of things, but the other thing is because we share targets, it's much cheaper to do 4HS within the consortium project than on its own. This is just because I'm terrible at remembering to do this, but I should, so first, like I say, I co-lead this with my co-PI, Michelle Kluver, who is also at Swinburne University. But the first and best thing that we did was to assemble a really excellent team. So these are our exec and what we call the science coordination team, who are responsible for all of the good things that I'm about to show you. I'll skip through this very quickly. All I really want to say with this is, before you do a spectroscopic survey, you have to pre-select your targets. 6 or 8 years ago when we were starting this, the VHS data, which is near-infrared imaging across the southern hemisphere, had the principal advantage of existing. So that's what we used for our input catalog. Since then, of course, legacy has, the legacy DR10 has happened, and very soon Rubin will also happen. But for the start, VHS was all we had to work with. The trouble is VHS is awful in just about every respect. So what you can see here is that it's extremely ugly and patchy and gross. We have made it good. So we've gone and basically pulled the whole Vista archive, reanalyzed the data, and we make it beautiful. I could talk for an hour on this, but I won't. The point that I'll make is we are a near-infrared selected sample to a depth of J of 18 with a color cut. This is just changed, actually, it should be 0.42. I've fixed it in other slides, but not this one, with the idea of pre-selecting low redshift galaxies. And compared to that really ugly slide, the thing that you should see is there are not many gaps in the yellow, and it's nice and smooth. We've done a good job there. How do you understand 4HS? The best way to understand 4HS, how many people know the gamma survey? A few. So it's gamma-like. It goes to a similar sort of depth. The gray here is the gamma sample. The colored points are what you get applying the 4HS selection to gamma, right? So the gray ones are the ones that you're missing. So 4HS has quite a similar stellar mass limit to gamma, is the point. Anything that you can do with gamma, you can do with 4HS. Does that make sense to everyone? Ish? Good? Okay. Right. So what do you do with 4 million low redshift galaxies across the sky? Our 3 key science goals are as follows. First is to map mass and motion across a gigaparsec to measure the cosmological growth of structure and gravity down to the variance limit. This is what I'll spend most of the next 10 minutes on. But that is a really good way to justify also at the same time building the galaxy census that you want to map galaxy demographics as a function of stellar mass and especially as a function of environment. So that's what I'll talk about in the last 5 minutes. But ultimately, like beyond the lifetime of the project, our ambition is to be the next Sloan, or really, the next Sloan in the south, to provide the definitive low redshift galaxy reference sample for eROSITA, LSST, Euclid, SKA, and all of the next generations of simulations. So I have to say it took me much longer than it should have to understand how you can measure peculiar velocities. So I'm going to spend 2 minutes doing that in the spirit of the cosmology school. I hope this isn't I hope this is useful. In the same way that, the Earth goes around the sun and stars go around in galaxies, galaxies go around in groups. The motions of galaxies within groups tell you about the gravitational field within the group. The motion of the groups themselves is set by the large-scale gravity, or the large-scale gravitational potential field, the field that the group is in. So if you can average the motion of many groups, what they're doing is responding to the large-scale structure, right? They're actually, that is large-scale structure in formation. So you can map material collapsing onto large-scale structure. And that's what this transition is supposed to be showing. So this is our local group seen in the context of the Laniakea superstructure. And then the idea is when you go out to very large scales, the universe should become isotropic. And so the goal is to map that progression from our group to large-scale structure to isotropy and test the cosmological, and hope that the cosmological principle holds. So how do you do this? The trick is that the observed redshift is the combination of the cosmological redshift and the Doppler redshift, right? You only observe this. You can't really disentangle these, right? Because redshifts are redshifts. But if you can measure a distance, then you can say what the cosmological redshift should be. That lets you subtract this away to isolate the peculiar velocity, right? So measuring a distance is the same thing as measuring a peculiar velocity if you know cosmology. That's the game. Oh, so how do you do that? So that's the game that 4HS wants to play. So how do you do that? 4HS is designed to do it via the fundamental plane. The idea is that if you can measure dynamics, that tells you something about the galaxy mass, right? So if you can see how fast the stars are moving, that tells you how big or how bright the galaxy should be. You measure how bright it looks, and the difference is the distance. Good? Good. That's the fundamental plane. Great. No, I will take a minute to say this. So the fundamental plane has been used for a very long time. It's common to hear fundamental plane people say that the coefficients that you get, right, the calibration that you get for the fundamental plane depends on the sample that you're using and how you choose to analyze it and what imaging you use, all of which is to say, I don't understand my systematics, right? This is a real problem. And so one of the really, so there has been a lot of work to try and address this, to try and fix this. But one of the really good things that 4HS is going to do is get lots of repeat observations to make sure that we understand the systematics in our velocity dispersion measurements, which is the observable that we're going to do. But the other thing is that, I need to explain this slide before I can get to that point. This is showing the current state of affairs. So these are all the velocity dispersion, all of the peculiar velocity measurements that exist, primarily from this thing called Cosmic Flows 4. This is primarily Tully-Fisher redshifts. You can see this is the Sloan footprint. This will be the DESI footprint. This is the 60FGS galaxy survey. This is what 4HS will do, which is, so to go from having of order 12,000 distance measurements to having something closer to 1 million. And the most important thing is, because 4HS will overlap with DESI in blue, with Sloan in the other blue, and especially with green, which is Wallaby, which is an SKA Pathfinder experiment, by making sure these surveys all speak to one another, we can get rid of the systematics problem, right? We can actually we can create consistency, we can cross-calibrate all the surveys together. No, I do need to say that. So this is doing this so we have a brighter and a bluer subsample for these distance measurements, and especially that we push really in close to the zone of avoidance. So someone was saying it's hard to do cosmology looking through the galaxy, but we can, because we have stellar surveys, because we have stellar partners. They're going there anyway, right? They need us to fill up their fibers. So it'd be crazy for us not to do this. Whereas if you're driving your own telescope, you said, I want to take a multi-object spectrograph and point it at the galactic plane, TACs say no. Cool. So, and the advantage, you just trust me on this, the advantage of choosing this sample is that for those galaxies in a very short amount of time, we just for free get the high signal to noise that we need for the velocity measurements. So we almost couldn't stop ourselves from doing this cosmology experiment, which just works out very nicely. This is the state of play. So this is the region of the universe over which the density field has been well measured, primarily from the 60F the 60F Galaxy Survey, which finished in 2014. Sloan pushed this out somewhat. DESI is making a big advance, but then 4HS is twice the area, nearly 10 times the volume. It's not about DESI versus 4HS, although 4HS wins, but don't tell DESI I said that. The real thing is that it's DESI plus 4HS, because together, what these do is give you a complete map of the volume, right? Which is the thing that's really important. The galaxies will measure the cosmic density field, the fundamental plane distances and velocities will measure the velocity field, so you can measure where the mass is and how the mass is responding, right? And what that lets you do is measure, that is the growth rate of structure. So this is showing how, this is the cosmological parameter that we're most interested in, F sigma 8. So this is how precise the measurement of F sigma 8 is. For 4HS in red, and we are a low redshift survey. DESI in blue, and so you can see that 4HS plus DESI gets a really nice measurement all the way along. What this is trying to show is these are the measurements of a different growth rate parameter, which I think is called G, big gamma. Yeah, I forget what this one is. But the point is that depending on your law of gravity, this parameter has there are very strong predictions for what this parameter should be. So if general relativity is correct, then you should get this gravitational index gamma of 0.55. And if other gravity is correct, you should see something else. So 4HS provides a way to measure gravity. The thing that I find really amazing is this will be the last peculiar velocity cosmology survey, because by the end of it, we will have measured every fundamental plane distance that there is in the southern hemisphere, right? Which I just find amazing, but it's true. There's a limit to how far you can measure fundamental plane distances. It's somewhere between 0.1 and 0.12, and we will have measured all of the early type galaxies to that distance. So in a very real sense, this is the culmination, the completion of a 50-year project of cosmology, which I still find amazing. Okay. In my last 5 minutes, I'm going to skip over extremely quickly the science that I really love the most. Why haven't we done this already? Don't we already know how galaxies work? I'm glad you asked. No. To map galaxy, the reason that mapping environment is so hard is, one, mass correlates with environment and everything correlates with mass. And so teasing out the environmental effects is hard. But the other reason it's hard is because no one knows what environment means, or certainly no one says what they think environment means. This plot's a mess. Don't worry, don't try and understand, it's not important that you understand what's plotted. Apart from each of these is a different way of measuring environment. The fact that they're scatter plots means they all measure different things, right? So before you can find out how important environment is, you first have to tell me what means environment. What you really have to do if you want to say that one of these factors matters more than the other is control for all the others, right? So the only way to uniquely disentangle which aspect of environment is important for which galaxy property is through overwhelming statistics. And that's the goal. Given the animation, I am going to explain this. This is our chances of putting a fiber on a target as a function of pairwise separation. How many people have heard of fiber collisions? Right, fiber collisions are really bad. They're where you can't get two fibers close to each other. And in Sloan, I think the fiber collision was at 10 arc minutes. I think that's here. So basically completeness dropped to like 40, 50% with these kinds of separations for Sloan. Here, what we're seeing is we've got about 93% globally, and this tiny little drop here at something like 15 arc seconds, yeah? So, oh my God, it's amazing, all right. We are going to find and characterize something like 100,000 galaxy groups. The reason that's amazing is simulations, many simulations, will produce this level of detail. So this is a Mach light cone. These are filaments. Each of these circles is a different group. Its size shows you its multiplicity. Its color in this one shows you its specific star formation rate. Here it's its H1 fraction. These three halos are basically the same. These two are forming stars, this one isn't. This one, well, these two have gas and this one doesn't, right? Simulations know about this. Simulations make predictions for why this is, but there are no data sets that can test predictions like this yet. That's why incorporated into the 4HS team is a dedicated simulation project to do these very large simulations to make these predictions, to test and calibrate. So following the gamma model, our ambition, the 4HS spectra are just the beginning. Then the goal is to combine the 4HS, they give you the redshifts, they give you group and environment metrics and halo masses, but then to combine that information with optical imaging from LSST to do SED fits like stellar masses, sizes and morphologies and lensing, to upgrade from VHS to Euclid, especially for lensing, to make full use of WISE, which is an all-sky infrared satellite for stellar masses, star formation, AGN diagnostics, radio from the SKA pathfinders, including Meerkat to SKA and eROSITA X-ray, you get that full census of all possible galaxy properties. If you haven't seen it, it's the perfect film. What I think we're working towards, especially with Euclid and LSST, is pictures like this. This is for the M82, the M81 group, right? So this is an M. This isn't even an NGC. This is an M group. And you can see you've got the stars. You've got the gas in red. You've got high velocity clouds and all sorts of things. This level of detail is only possible for Messier galaxies currently. I think with LSST plus Euclid, we can get this level of detail for 100,000 groups across the whole sky. Right? How you make use of those data gives me the deep fears, but to have the data to begin starting to think about it is, I think, where we're going. 4HS first, okay, status, this is real data. These are real galaxies now, real spectra. So Foremost had its first light in October, oh gosh, that's almost a year ago. So this was the first light image. You can see there's a galaxy spectrum. The lines are amazing. The spectral resolution is so high, it's 8,000 or something. When we saw the first redshifts, you're like, why are these, what's crazy about these galaxies? They all have these strong emission lines. Everything has these booming emission lines. It was the first time that we'd seen them resolved. Yeah, it's like the JWST of spectra. Okay, this is a nice, so we had our survey program validation, which isn't early science. It's not science commissioning. People get angry if you call it those things, but that's basically what it is. That was a couple of months ago. This is showing 3,000 spectra just stacked in order of redshift, and you can see redshifting works. This is one of my favorites. I picked this galaxy truly at random. This is a galaxy at a galactic latitude of like 8, right, in the Vela supercluster. You can see it's really crowded. Here, signal to noise of 16. The velocity dispersion is beautifully measured. This is showing that we really can do this peculiar velocity science in close to the plane. Just to really, that's the one we're looking at, right? These are crazy bright sources around, okay? So where are we? The SPV completed a couple of months ago. We had our final operations rehearsal a couple of weeks ago. The operation readiness review, so signing off the documents and all of those sorts of things, is anticipated in 5 or 6 weeks. There will be I love that they call it the burn-in phase. That's 2 weeks of survey operations, and then they'll just dump the data. That's anticipated early mid-September, so we begin in about 6 weeks. The first full year of data will be released in early 2029. For cosmology, right, whatever the astrophysics, low redshift science is driven by or limited by the availability of spectroscopic redshifts. Wrong one. I said I'd be good, but I've been terrible, I'm sorry. Right, so what will we deliver? 4.5 million galaxy redshifts? Good grief. Forgive me. How about now? Okay. 800 redshift independent distance measurements, 650,000 groups. The best thing is you get group average redshifts for all of these groups, as well as group average distances for all of these groups. If you want to do, and full all-sky, bulk flow modeling, peculiar velocity modeling. So especially if you're interested in low redshift supernovae or gravitational waves, 4HS will eliminate the largest systematic effect, which is the peculiar velocities. So 4HS enables LIGO cosmology. This is my final slide. The things that you need to know is that we're near infrared selected with a density of about 325 targets per square degree, that working within the foremost model is challenging, but extremely worthwhile. And I'm sorry for going overboard, and I'll take some questions, if I have time.
Thank you for the wonderful talk. 4HS is awesome.
Sold.
Now, so on the F sigma 8 side,
Yep.
we often worry about the distance systematics, both from fundamental plane and type 1As. What are the kind of redshift systematics that we might also be worried about? Because we sometimes just think that host redshifts are just perfect. I know you said that you're cross-calibrating the other surveys, so what are the kinds of things? Is it more air mass dependent stuff? What kind of things are you worried about?
Yeah, so for fundamental plane and for supernovae, they're very different, right? And for fundamental plane and Tully-Fisher, they're also quite different. The thing that's hard for fundamental plane is that velocity dispersion isn't really a uniquely defined measure, right? Because you can imagine that if you mapped a velocity dispersion profile, right, it changes. And so if you put down a fiber and the seeing changes, your velocity dispersion changes. Or if you have the same galaxy at different distances, you measure different velocity dispersions, right? So that's the nightmare. And so that's what makes it really hard to compare across samples. One thing we're doing is we're getting repeat observations at very different conditions for oodles of galaxies to try and figure out those observational effects. Especially matching with DESI is super valuable because they're at different latitudes. So targets are seen at different air masses. So it's only combining north and south that you can really get the different air masses. You can get the air mass effects out, if that makes sense, right? And then there's all the other stuff. But the good thing is, once we have that under control, or as under control as we can, and I have to say the early data are like, oh, I think John Lucy said it has taken us 10 or 15 years to get to this point with most other surveys, right? It's amazing how we've learned all of these lessons. But once you have that, then you can compare the supernovae to that, right? And you can compare the Tully-Fisher to that, and you can establish a really high quality standard. I hope that was a long answer, but I hope I got there.
All right, one more, and while I run this over, I'm just gonna ask quick,
Yeah.
Why Tully-Fisher and why not Tully-Fisher? What's wrong with Tully-Fisher?
I've got a single fiber, and so Tully-Fisher from a single fiber is hard. There is a supplemental program inspired, DESI's doing a similar thing, to put fibers out on the sides of galaxies, which is in principle doable, but really hard. It's a bit sketchy, but we'll give it a go. But Tully-Fisher is better done with radio data. But bringing the two together is awesome, especially in groups, right? If you can get a fundamental plane distance and a Tully-Fisher distance in the same group, you can bring them together.
Hi, thanks a lot. Very cool. Two quick questions. One, to reconstruct essentially the cosmic neighborhood. That was kind of one of the main aims you were pitching for. Is there any value in going deeper to lower mass objects, or you think essentially with these steps, that's what we can get, and improving over this is not that feasible?
Something I'm really excited in is the idea of constrained simulations, where you Monte Carlo, yeah, absolutely. So there, I think once you get to a few satellites, I think they're already mapping the halo dynamics as well as you can. And so I don't know how much extra value there is in mapping down, in going down, to those really low scrappy things. Because I think then also the astrophysics gets hard, and that's where you're starting to learn as much about the simulations as you are about the universe. So I think the information in constrained simulations really comes from the large scale information rather than that subhalo stuff. But that subhalo stuff is going to encode all sorts of good galaxy formation things too, right? I'm just not certain that a local volume constrained simulation is the best way to get at that inner halo stuff.
Thank you very much. Let's thank the speaker again.